Hello everyone. We are from SRM Institute of Science and Technology, Department of Computer Science and Engineering. I'm Sahitya Krishna Kumar.
I'm Shivani.
We are here to present on the topic multi-core processors. So let's get started with the concept of parallelism. So what is parallelism? It is a co-computing concept that enables a system to execute multiple tasks at the same time. So by dividing tasks across multiple processor cores, parallelism improves efficiency, processing speed, and overall system performance. It's essential in fields that demand high-performing computing, like data science, machine learning, and etc. There are two types of parallelism: data parallelism, cluster parallelism. So what is data parallelism? Data parallelism involves breaking down a large data set into smaller chunks, then processing each chunk in parallel across multiple processors. Uh, each processor performs the same operations on the assigned portion of data by dividing the workload. This way, data parallelism reduces the time it takes to process large data sets. Example is if we take a large image and we want to apply a filter on the image. So by taking data parallelism, the image can be split into different sections and each processor will be working on the different part of the image. So after the processor applies the filter to the assigned section and the image is again reconstructed. So this is an example of data parallelism. And what are the ideal use cases are situations where operation needs to be applied repeatedly across elements, like for example, matrix operations, or in image or video processing, etc. Task parallelism is also known as functional parallelism. Here, the program is divided into independent tasks that can run concurrently, and each processor executes a different task rather than processing separate chunks of data. Task parallelism is beneficial where tasks are logically distinct but may have dependencies that define the order of concurrency with which they are executed. So the example of task parallelism is, let us consider a video rendering program. So we need to encode both the audio and the video. One processor could handle audio encoding while the other manages video frame processing. These tasks are very different in function but can occur simultaneously, improving the overall speed and efficiency of the rendering. The ideal use cases for task parallelism is that we can use this in situations where tasks are performed in parallel without being affected by each other, or in pipeline processing. The tasks can be processed in different stages, and each state can be handled by a different processor. So let's get into our main concept, multi-core processors. What is a multi-core processor? A multi-core processor incorporates more than one processing unit or a core on a single integrated circuit. Each core is capable of reading and executing program instructions, meaning that the processor can handle multiple operations simultaneously. So unlike our traditional single core processors, in a traditional single core processor, the process instructions are given after one after the other. But in multi-core processors, we can manage multiple processes in parallel. This not only boosts processing efficiency, but also optimizes resource allocation for better performance. What are the importance of multi-core processors? Multi-core performance. That is, with multi-core working together, a multi-core CPU can process more data and complete tasks faster than a single core processor. This means users experience quicker application response times, better performance for intensive tasks, like, for example, gaming or video editing. Reliability. Reliability is like when a multi-core processor offers improved reliability by isolating processes across different cores. That is, if we encounter a software crash in one core, the other core remain unaffected, allowing the system to continue running other tasks without any interruption. The next thing is multi-threading. Multi-threading is where many modern applications today are designed for multi-threading, where a single application is split its workload into multiple threads that run in parallel. Multi-core processors can assign each thread to a different core, ensuring smooth interaction and faster processing within the application. Next is multitasking. Multitasking is multi-core processors make multitasking very seamless, allowing multiple applications to run without slowing down. For instance, let's take a user. He could stream a video, run an antivirus scan, and also browse the internet simultaneously without noticeable performance degradation. And last is power consumption. Multi-core processors are designed for greater energy efficiency. Like each core consumes less power than a single core processor, equivalent output. The ability to distribute tasks across cores also means that each core can operate at a lower clock speed while maintaining performance, leading to lower heat output, reduced power usage. So here is a diagram, or here's a picture that depicts a multi-core processor. Now let's see how does a multi-core processor works. A multi-core processor works by integrating multiple processing units into a single chip that we know. And here each core operates independently and is essentially a full processor in its own right, meaning it has its own ALU, control unit, and memory. Now let's break down to see how each component works. Independent cores. Each core within a multi-core processor is independent, capable of executing its own instructions. Think of each core as a mini processor within the large processor. Each core has its own ALU where it performs arithmetic and logic operations and a control unit that directs its actions. Most importantly, each core typically has a private cache, usually L1 and sometimes L2 cache, a small high-speed memory that stores frequently accessed data to reduce the time needed to access the memory. This allows each core to perform operations without interference from other cores. Parallel processing. Parallel processing is the main advantage of multi-core processors. It allows multiple cores to work on different parts of a task simultaneously, increasing efficiency and speed. For instance, in applications that can be divided into smaller parts, for example, video editing, each part can be assigned to a different core, allowing these tasks to run at the same time. So this process is called as parallelization. Not every task is parallelizable. Some tasks must be completed in a sequence. However, many modern applications, particularly those that require intensive computation, are designed to benefit from parallel processing. And multi-threading. Each core can execute threads, sequences of instructions necessary for a program to function with simultaneous multi-threading. A technology seen in processors like Intel's hyper-threading, a single core can manage multiple threads. Simultaneous multi-threading effectively doubles the number of threads the processor can handle without adding additional physical cores. For instance, a quad-core processor with a simultaneous multi-threading program can handle up to 8 threads, enabling it to process more tasks at once, boosting performance in highly parallel tasks. Multi-threading allows each core to keep working on different threads while waiting for resources like data from memory available, improving core utilization. Shared and dedicated resources. Each core in a multi-core processor has dedicated caches for fast data access. Some multi-core processors also share a larger L3 cache among the cores. So this shared cache stores common data and instruction, facilitating communication between the cores and preventing the need to retrieve the same data multiple times. Additionally, a memory controller shared among the cores also manages the access to the main memory. This allows the core to access data quickly and efficiently, minimizing bottlenecks when several cores need to access the same memory. Task scheduling and load balancing. The operating system has a task scheduler, which is responsible for assigning tasks to different cores. The OS makes these decisions based on the workload and the available resources, ensuring that the tasks are spread evenly across the cores. And load balancing is also crucial because if one core is overloaded with tasks while the other remain idle, the performance of the processor decreases. The OS continuously monitors each core's load and redistributes tasks as needed to avoid any single core becoming a bottleneck. Now let's see an example of multi-core processing in action. So we have taken a video editing application. Let's look of how a video editing application may utilize a multi-core processor. A video editing program often involves multiple tasks that can be handled independently, like encoding, decoding, filtering, rendering frames and all. So the OS task scheduler assigns each of these tasks to a separate core, allowing them to run simultaneously. For example, core 1 might be handling encoding, core 2 might be handling decoding, etc. While within each of these tasks, if the processor supports multi-threading, each core may further divide its workload across multiple threads. This setup drastically reduces the time it takes to complete the complex tasks compared to a single core processor. In a single core processor, each task would be handled in a sequentially, it would take a long time. Now let's look into homogeneous multiprocessors. A homogeneous multi-core processor is a type of multi-core processor where each core is identical in terms of architecture, performance capabilities, and instruction set. This means that every core within the processor has the same processing power, functionality, and capability to perform tasks at the same speed and efficiency. This uniformity across cores offers unique advantages in applications where parallel processing is crucial as it allows tasks to be distributed evenly across all cores. A homogeneous multi-core processor is built for environments where the tasks can be split and processed in parallel by multiple cores that work in a synchrony. Commonly, the cores in these processors are general purpose central processing units capable of running a single multi-core operation system. Now, what are the key characteristics of homogeneous multi-core processors? Uniform cores. Since all cores are identical, task distributions become very straightforward. Any task can be processed by any core without concern for differences in speed or processing capability. So this is very beneficial in situations where tasks need to be dynamically assigned across cores. Next is parallel processing efficiency. Homogeneous multi-core processor excel in parallel workloads because each core can handle a portion of tasks simultaneously. For example, applications that involve repeated computations can be split into multiple parts. For example, scientific stimulations or batch processing, for the matter of fact, benefit significantly from this uniform structure. Next is ease of development. From a software perspective, homogeneous systems are easier to design and implement because developers don't need to account for variations between cores. This uniformity not only reduces the complexity of the software, but also simplifies the development of compilers and operating systems, making homogeneous multi-core processors suitable for applications that require consistent performance across all the cores. Finally, load balancing. Load balancing is simpler because all cores perform identically. Operating system can distribute the tasks across cores without having any factor in performance differences. This uniform load distribution ensures that all cores operate at optimal efficiency, preventing bottlenecks and maintaining balanced workload.
Now we will look into the homogeneous multi-core processor architecture. So the diagram of homogeneous multi-core processor illustrates a processor built from multiple identity cores, all within a single chip. So let's walk through the main components you would typically see in such diagram. So the first one is cores. So speaking about the cores, we have the identical processing cores. So the key feature of homogeneous multi-core processor is that every core, whether it's core 1, core 2, or core 3, is identical. This means that they are designed in the same way. They have the same processing power and share the same instruction set. Because of this uniformity, all tasks can be assigned to any one core and the performance will remain consistent. Next, we have the execution unit. So each core contains execution unit like the arithmetic logic unit and the floating point unit. The arithmetic logic unit performs arithmetic and logical operations, while the floating point unit handles complex calculations such as those involving decimals. In such homogeneous architecture, each core has identical execution unit, which ensures that no matter which processor is processing a task, it does so with the same speed and precision. This uniformity is crucial for predictable performance and simplifies the design and programming of the system. Next, we have the cache levels. Uh, the L1 cache level to speed up data access. Each core is equipped with its own dedicated L1 cache. The L1 cache is often divided into two parts. The L1 instruction cache, which stores frequently used instructions, and the L1 data cache, which holds frequently accessed data. So the purpose of having this dedicated cache is to reduce the time each core spends fetching data from main memory, which is slower. By having frequently used data and instruction flows at hand, the cores can perform computation faster and more efficiently. And then we have the L2 cache. So each core in the processor often has a private level 2 cache, which is larger than the L1 cache. Thinking it as a secondary storage layer for frequently accessed data. If the L1 cache doesn't have the data a core needs, it will check the L2 cache before going to main memory. So why this matters is because having this extra layer of cache, the processor reduces the number of times data needs to be fetched from the much slower main memory, speeding up the processing and reducing delays. Then we have the L3 cache, which is shared. Many multi-core processors include a shared level L3. Unlike the L1 and L2 cache, which are private individual cores, the L3 cache is accessed by the all cores. It serves as a common pool of data and instructions that the cores might use, promoting efficient data sharing and communication. So why we need this? For example, if the core one process some data and core two needs the same data, shortly after the core two can access it from the shared L3 cache instead of retrieving it from the main memory, saving time and improving performance. Then the next we have the interconnect of bus system. All the cores in the processor along with the shared resources like the L3 cache and the multi-memory controller connect to an interconnect network or bus system. This network allows the cores to communicate with each other with the memory subsystem efficiently. And then we have the memory controller. So speaking about the memory controller is a crucial component that manages the flow of data between the processor and the main memory. So here the main memory is we have the RAM. So when any of the cores need to fetch data from or store data to the main memory, the memory controller handles these requests and ensures that they are executed efficiently. Um, so to understand this, imagine the memory controller has a traffic cop directing cars. So here the cars are the data request at a busy intersection, making sure everything flows smoothly without crash or long delays. Then the next topic is we have is that input-output interface. So speaking about the input and output interface, are connections that link the process to external components. So such as storage device, input device, output device, and network interface. So we need this interface to interact with the outside world. Uh, that is, we can interact with the system and we know what's happening. For example, when you have save a file, the process sends data to storage device through the I/O interface. So that is how the input-output interface work. Next, we have the APP. So in the context of multi-core processor, APP actually stands for application. So these are the software programs or processes running on the processor. In a multi-core environment, each core can run different applications simultaneously or handle multiple threads of the same application. So what is use of APP in homogeneous and what is the advantages? Since all the cores are identical in homogeneous multi-core processor, they can seamlessly divide up tasks, whether the means run multiple separation application or parallelizing parts of a single complex application. Next is the host operating system. The host operating system is crucial software that manages all the hardware resources in the system, including the processor cores, memory, storage, and I/O devices. The OS coordinates how applications interact with processor and other components. So Why we need this is for resource management. The OS is responsible for distributing tasks to the different processor cores. It is also used in scheduling and load balancing, and then a simplified analogy. And then, so this explains how the processor interacts with the external components through the IO interface, and how it handles multiple applications in multi-core setup, and how the OS manages and coordinates everything. Then the next part is how what we have is that how all this works together in homogeneous multi-core processor. Uh, so so understanding is how tasks are distributed, data is accessed, and core communicates with the will give a complete picture to the multi-core architecture. So task distribution is that the OS operating system plays a center role in managing all the tasks. So when you run a multiple applications or when a single application has many tasks, the OS decides how to distribute these tasks across the available cores. So example, if you're running a video editing program while browsing the internet, the OS might allocate the video processing task to one core and the browser task to another, allowing both to run smoothly without slowing each other down. Then we have data access and cache management. When a core needs a data to execute a task, it first looks on in its L1 cache. Since the L1 is the fastest and closest to the core, finding the data here speeds up processing significantly. If the required data is in the L1 cache, the core checks in the L2, which is still relatively fast but large. If the data is in an L2 either, the core will look in the shared L3 cores. So the cache hierarchy is very efficient. This multi-level cache system minimizes the time core spends waiting for a data. Then we have the parallel processing and communication. So in a homogeneous multi-core processor, all the cores are identical. They can divide a task for parallel processing. When a single application can be broken down into smaller parts, the OS can assign these parts to different cores to run simultaneously. Then we have the intercore coordination. So if a core needs to share data, the OS facilitates using shared caches and intercore communication pathways, ensuring the consistency and synchronization. So next topic we have is that the heterogeneous multi-core processor. So speaking about the heterogeneous multi-core processor, a heterogeneous multi-core processor is especially a type of processor that includes different kinds of core on the same chip. Unlike the homogeneous multi-core processor, where all the cores are identical, a heterogeneous SAS setup mixes cores with various performance and power characteristics. This design allows the processor to optimize efficiency and performance by assigning tasks to the most appropriate core type. So, speaking about its key characteristics, it has different cores. The one is the high performance cores. This is called as the big cores, and the power efficient cores, commonly referred to as little cores. So now let's look into the high performance cores, which is the big cores. So high performance cores are designed to speed and can handle demanding intensive processing tasks. They operate on high clock speeds and optimized to deliver maximum performance, making them ideal for heavy computational work. So while these this may, and the use case of all these things is high performance cores come into play for acting like gaming, video rendering, and running complex applications that require fast and powerful consumption. Next we have is that Next, we have is little cores. So speaking about little cores, which is power efficient cores. So power efficient cores, these cores are operate at low speeds compared to the high performance cores, but are highly efficient when it comes to handling less demanding tasks. So what is its purposes? These cores are identical for background processes or simple tasks that do not require a lot of computational power. And then we have the task assignment based on workload. See, the OS plays a key role in managing how tasks are distributed among these cores. It monitors the requirements of each task and decides which type of core should handle it. Um, and the next we have is that energy efficiency and performance balancing. See, the goal of heterogeneous multi-core processor is to strike a balance between energy efficiency and high performance by relying on power efficient cores for less demanding tasks. The system can conserve energy and reduce heat output. So what are these benefits is this energy saving strategy is especially beneficial for mobile devices where extending battery life is crucial. And then and then we have the dynamic task switching. So speaking about this, what dynamic task switching means that it allows the operating system to move a task from one type of code to another, depending on the task changing demands. This flexibility ensures that the system can respond quickly to new requirements and use its resource as efficiently as possible. Then we have the so speaking about the examples, we have Intel Alder Lake processor. So how it helps is that so Intel Alder's one is that a popular real world example. This processor have mix of performance and core efficient cores. So we can give an example scenario. When you are using a Alder Lake powered laptop, the E cores can keep the system running efficiently when you are just typing a document or browsing the web. But if you open a complex 3D modeling software, the P cores activate to provide the power needed for a smooth experience. So next is that we have the embedded system. It's so crucial in an embedded system where the power performance constraints are often strict. These systems are used in special environments like automated computers, industries, and or smart appliances. So what is the next? So speaking about the heterogeneous multi-core architecture. So this is a diagram representing the heterogeneous multi-core architecture. There are certain similarities between the homogeneous and heterogeneous. So now we look into detail about the heterogeneous. So in heterogeneous multi-core architecture, it works upon the slave master concept, which means that in a heterogeneous multiprocessor, the master slave concept is a model designed to efficiently manage and execute tasks using cores with different capabilities. So in this model, there's a division of roles between the cores, with one acting as the master core and other acting as the slave cores. So, so here we can look into the central role of the master core, which we can assume as the manager. So here the central control is the master control. A master core often a powerful and high performance core is responsible for overall control and coordination of the system. The next and then it has the task distribution with it. So the master core assigns specific tasks to slave cores and based on either capabilities and current workload. For example, in the ARM big little system, the master core can distribute lightweight tasks to little cores and reserve complex high power tasks for itself or other high performance core. And next we have is that in heterogeneous architecture is so the role of is we can speak about the cores. So in the cores, we have a high performance core, which is called as big cores, and power efficient cores, which is a little cores. As we seen earlier, so these cores, the high performance core is used significantly for computational power. They're capable of executing complex operation quickly, but tend to consume more energy. And speaking about the little cores, they operate at a lower frequency and consume less power, extending battery life in mobile devices and reducing heat generation in laptops. So, and then we have and then we have the interconnection and communication. So, speaking about the interconnection and communication, uh, uh, Speaking about the overview, heterogeneous multiprocessor system, the interconnection refers to the methods used to link different cores, enabling them to communicate and share data effectively. Given the diverse performance and power characteristics of the cores, and interconnects must be designed to optimize data while minimizing latency. So types of interconnects, we can see that we have sophisticated interconnects, mesh interconnects, point-to-point networks. The mesh interconnectors these allows cores to connect multiple neighboring cores, providing multiple pathways for data to travel. And point-to-point networks, these networks link cores directly, facilitating high-speed data transfer between individual cores. Then we have the hierarchy interconnect is that uh, in this model, a high performance core are prioritized for data access, driving preferential treatment in data transfer. So this ensures that the performance crucial tasks have quick access to the data they need without being slowed down by the less demanding workloads. And then we have the pros and cons. We have the pros and cons of homogeneous. So looking into the pros and cons of multi-core process. So here pros is the advantage. Homogeneous multi-core process has the simplified design compared to a heterogeneous. So the uniformity of these cores leads to simple architecture. Since all the cores are identical, the design and implementation becomes more straightforward, making it easy to develop and maintain the processor. And then it has uniform performance. All cores provide the same performance, ideal for parallel tasks. So this uniformity ensures that the tasks are executed consistently across the cores. So then we have the consistent task allocation. The OS can assign any task to any core. So this flexibility simplifies task management and scheduling, as the OS can distribute workloads evenly without intrinsic decision-making process. And speaking about the cons, the disadvantages of the homogeneous multi-core processor, low power efficiency. So uniform cores leads to higher power consumption, especially for light tasks. So this leads to higher energy consumption, which can be determining, especially in environments where power efficiency is crucial. And then less flexibility. Lacks power saving options for mixed workloads. This inflexibility can result in inefficient resource utilization. And then we have not ideal for mobile devices. So higher power uses makes them less suited for battery dependent devices. So then speaking about the heterogeneous multi-core processor, uh, the pros, the advantages of the heterogeneous, it's power efficient. Cores handle light tasks, it saves energy. By offloading these less demanding tasks to lower power cores, the overall energy consumption is reduced, extending the battery life. And in the flexibility of performance scaling, high performance cores handle the demanding tasks, while low power cores handle lighter ones. So, and in specialized processing, often includes GPU or AI cores for specified tasks, boosting performance. So what are this benefit is this flexibility ensures that the resources are used optimally, providing high performance power when needed without wasting energy on tasks that do not require it. And the cons, the complex scheduling, uh, it has a complex scheduling requires advanced scheduling to match task to core capability. So the complexity of can lead to overhead where the operating system spends considerably time depending the most efficient allocation of tasks. And then higher design complexity, uh, the costlier to design due to diverse core types. And then we have the software compatibility. Some application may not fully utilize mixed cores. Then, which architecture is preferred? So, speaking of this, whether we prefer homogeneous or heterogeneous, homogeneous is it depends only about the environment, what situation are we in. So, homogeneous processes that It has uniform and predictable performance. Uh, it can be used in traditional servers in data centers where homogeneous architectures are often deployed. And then scientific computing, application that requires extensive numerical computations benefit from the uniform performance. Desktop and data centers where the system do not typically have stricter power efficiency requirements, allowing homogeneous processor to be favored. And then we have heterogeneous processors. Uh, in heterogeneous processor, there's power efficiency and adaptability. So heterogeneous are preferred in environments where power efficiency is primarily concerned, especially in device that operates on battery power. This ability to adapt and varying workloads demanding makes them ideal for mobile applications. So it's commonly used in modern laptops, mixed workload environments, and especially in mobile devices and tablets. And then we have in summary. That's it. So speaking about summary, giving a summary to what about the multi-core architectures. Uh, both of them are ideal, and both of them they play a very crucial role in today's technology. So homogeneous multi-core processor has ideal applications, and they have so much design benefits in them. And in heterogeneous multi-core processor, it is very flexible and efficient, and they are targeted very use case. They are very beneficial for again for mobile phones, laptops. So that's it. So in conclusion, we can say that the choice between the homogeneous and heterogeneous multi-core processor hinges on the specific demands of the application environment. Homogeneous processor provide consistency and reliability for uniform workloads, while heterogeneous processors deliver flexibility and efficiency for diverse tasks, making them particularly suitable for modern mobile and consumer device. So thank you.